All right, I got about 3 minutes after. I think we'll go ahead and get started. If others trickle in, obviously, I'll have them, just join and put everybody on mute. So, my name is Rich Solte. I'm the VP of Sales with Prolim. Appreciate everybody joining this morning. We're going to have some folks from Siemens talk about the SimCenter portfolio and simulation for designers. So I'd like to introduce Richard Ozaki and Michael Senedak and Emmett Thalman from Siemens. And I'm going to turn it over to Richard for our presentation this morning. What I'd ask is during the presentation, if you have any questions, please send them to me through the chat. And let's hold the questions to the end. That way we don't disrupt the presenter. And then we'll answer your questions at the tail end. Thanks, everyone. Over to you, Richard.
All right, thanks, Rich. And just to let everyone know, this looks like this is being recorded. I think that's a legal requirement. But anyway, jumping in. So today's topic we're going to be discussing is simulation for designers. So here at Siemens, we are very big on the digital twin, and I like to think a lot of our customers have adopted the physical digital twin quite well, i.e., the CAD, managing all of that data. That's been understood and adopted very, very well. What hasn't been adopted as well is the functional digital twin. Once you design something, how can we understand how it performs? How can we understand various different loading parameters, and how can we store that data in a way that is useful and easily extracted again for use and for performing, optimization perhaps. So today's topic is really talking about enabling that 3D CAE or computer aided engineering for CAD engineers. Historically, it's been something an analyst would perform, simulation, but more and more it's becoming achievable for CAD designers to do basic run-of-the-mill type simulations to really understand how your products are going to perform. So with that, just click on to the next one. So what is CAE? Well, CAE is, I'm sure you've seen many pictures, I've got a couple of videos on the screen here, but CAE is really simulating your mechanically designed products to understand how they're going to perform. Okay, so it allows you to virtually evaluate all design proposals before testing. Okay, so if we take an example of the gears on the top there, what's going to be the most optimum pitch on the gears, or the angle on the gears, or maybe those holes in the middle for lightening or reducing inertial mass? What's going to be the best combination there? We can do all of that virtually without having to prototype anything, wait for parts to come back from China or your manufacturing center, test them, which is a long, expensive process. We can do all of that virtually now, and a wide range of conditions can be performed as well. Another benefit is that we can explore the design space for the optimum. Okay, so doing a lot of what-if studies, and which can be impractical in lab testing, is very, very beneficial. Okay, and if there is a failure, we can quickly catch those earlier on. Again, before we move to tooling or prototyping, we can catch those earlier on, fix them, and then reduce the time and cost associated with physical testing as well. So this really drives a get it right first time philosophy. So those two videos there, the top one is what we call a structural simulation. It's a structural dynamic simulation. And then the bottom one is a CFD or fluid simulation. These are the two main simulation disciplines that we're going to be discussing today. So why perform simulation? Well, I've kind of touched on that a little bit, but it really reduces the need for physical prototypes. They're very expensive and take time to create. This then in turn reduces costs, not just of the physical prototypes, but also lab testing costs. And it really speeds up the development process. So this is really the three main ROIs that you achieve through performing simulation. And as I mentioned, historically, it's been something that an analyst would do. You'd need like a PhD to run some pretty advanced CFD simulations. But more and more, with the advancing power of modern computers and the proliferation of CAD and people using CAD, we're pushing that more and more down into the designer level. Just to expand on that a little bit, if we think about the design process of a product, concept design, production, and maintenance, the cost of making changes increases dramatically as we move more and more towards final sign-off. Okay, if we're doing simulation towards the right at the validation phase, that's historically how it's been used. But if you catch something at the validation phase, it's too late. It's still going to cost you a lot to make those changes. So if we can shift left, perform front loading at the earlier concept and design phase, that's going to have a lot of benefit in terms of, cost of fixing problems. And also, there's going to be a lot more room for making those changes because, again, nothing has been fully signed off and published yet. Okay, so we're really trying to democratize the simulation process. So what are some of the historical concerns and challenges with simulation? Well, here's some of the things I've heard from CAD engineers in the past. It takes years to become an analyst. I'm not trained to do simulation. We don't trust the designer to deliver accurate simulation results. It's too time consuming. This is something we've heard a lot in the past, and really, I really strongly believe that our tools can address a lot of these problems and get designers to do, like I said, not the very high level simulations, but really sort of, run of the mill part sub-assembly type simulations. It really isn't a big deal any longer. So simulation today is a bottleneck. Okay, normally there will be some simulation team that will be working on a revision of the assembly. By the time they've delivered the results and we understand how it performs, the design's moved on significantly. Okay, and if we do that again, by the time we're at design 6, the simulation is very much out of sync with the actual revision of the assembly. So again, historically, this has been an issue, especially when you're using things like neutral file formats. If you're providing a step file to your design team, there's no revision control. There's no history data to that CAD. It can be very difficult to work with it as it's a neutral file format. It's a dumb solid, and it can take time to mesh and fix things before getting to a result. So just wanted to highlight that oftentimes the design and the simulation does not stay in sync. It can be a bottleneck, and by the time you got the results, the design's moved on, 3 or 4 revisions potentially. So at this point, I'm going to hand over to my colleague Mike, who will introduce himself very briefly and do the next few slides.
Great. Thank you, Richard. So Mike Senedak, I'm with Siemens as well. I'm part of the team that Richard works on. So we support our partners, and my background is in design, engineering. So, I've seen a lot of the tasks and the problems and issues that Richard is talking about. And so I think this graphic really illustrates that from the standpoint of, designers, their job is head down, get the parts modeled, get the drawings made, get it out to manufacturing. And so, when simulation, if you have a person or a team to do that, that information gets pushed over the wall. And like Richard showed in the previous slide, those information, it becomes out of sync very quickly because design iterations are happening quickly prior to release and then maybe even once it's launched. And so you're losing that. So go ahead with the build, Richard. So as we go through that, right, it's how do we get those two tighter together? How do we get them pulled together so that we don't have as many iterations that are not matching what the physical part is? And so with that, that's really where our strategy comes in to help our customers use our tools earlier in the design phase and be able to start to break down that barrier, start to get a better idea of what the performance is of our product. So next. So as we go in, some things that are really key to making this happen. Designers are comfortable with the geometry. They know how it was built. They know how to change it and modify it. And so our simulation tools give you that best in class geometry editing capability. You can go in, you have access, both to parameters and even models that don't have history that may come in through our multi-CAD support, right? So we talk about the multi-CAD, yes, most design houses, they're going to have, a particular CAD, their primary CAD tool, but they might be working and collaborating with a supplier or a customer that has different CAD tools. So all of that different data coming in is being able to handle that, work with that, make changes. And those are two foundational elements of our CAE solutions. And then also that associativity to the design change, because we know whether it's in the prototyping phase or even once a product gets released, design changes are coming through and you want to be able to confirm, yes, it's going to perform and act the way that we assume based on our simulation that's going to happen properly. So next one, Richard. So when we talk about how can we easily work with that geometry, Synchronous technology is at the core of this, so it allows us to quickly, easily modify parts regardless of whether it's a history-based model, whether it comes in through a translated, a step file, parasolid, something like that. And so through our selection intent, we're able to pick up on, like you see in the left image, what is, bosses, ribs, pockets, all those different shapes, so that the designer can easily select it and make those changes to see what if we make it thicker? What if we thin it out? What if we move the location and see what the simulation tells us, right? Are we doing things better or worse? So that's the key, one of the keys to help, from a designer, hey, I can work with whatever geometry I have and make those changes and drive those updates. Next. So one of those tasks for the designer up front is it's when you're doing simulation, it's not just taking the 3D solid, putting a 3D mesh on it and solving it. That's not always the case, right? A lot of tools out there will force you down that path, right? Just put a 3D mesh on it and get some results. But with our solution, we provide a lot of tools to help abstract or what we call idealize the geometry. And so, for instance, with our advanced mid-surfacing capabilities, when you do sheet metal parts, really don't want to put that through a 3D mesh. You want to get the mid-surface and do a 2D surface mesh with that because of the way to get the accurate results out of that, you want to be able to have those tools. So we provide that. Things like defeaturing, right? So when you have a part, if you have a lot of tiny holes, small blends, those are things usually you want to remove from the model. And you want to do that quickly because if you leave those in, it creates more mesh elements, a lot higher count, and all that does is draw out the simulation, and you really aren't going to get the benefit from that. So we provide a lot of tools to go in, pick the part, remove all the holes out of that, or for a particular size. Things like splitting up the bodies. So there are some type of mesh that you might want to create a swept mesh. You want to be able to divide up that body to be able to quickly build those sections of the mesh. And so we have very powerful tools to efficiently do that. Same thing you saw with the fluid domain, right? So of the tractor cab, or in this case of the car on the screen. Think about the time that you might have to do that under traditional tools. Well, with our capability, we can quickly get to the blue shape, which is the air volume or the fluid volume inside of that particular product. So a lot of tools to help you do that work very easily for both a designer and an analyst. Next. So once the designer has gone through that process of idealizing, preparing for simulation, the idea is now we want to be able to put, a good mesh on the part and do that quickly and efficiently and produce good elements. And so this is the same thing here, is the fact that you also need different element types depending on the problem you're trying to solve. And so our solutions provide you, one-dimensional, two-dimensional, and 3D meshing capabilities. And we've done a lot of benchmarking around this to be as efficient and the best mesher out on the marketplace. And so other things that are important is, your mesh controls. A lot of designer level tools, they just want to automate that and take that control away from the designer. And so in our tools, we give you that capability to go in and refine that as you're working. And then ultimately, being associative to that geometry. So when the design change comes, not if, and being able to update the mesh and ultimately your loads and boundary conditions, you don't want to have to start from scratch. You don't want to have to redo that work. And that's really where we put a lot of effort into our solution. Next. So just to give you a quick idea of what are those different types, the 1D mesh is something, if you guys have frames, if you're piping, tubing, that type of thing, where you're having the really develop the 1D, which is the center line, right? Something like you would do with a sketch. You put that on and then define the type of cross section that goes on that. 2D meshing, where you may have, like we talked about, the sheet metal parts, where you would do the mid surface for that, or you could also use that where we call a mapped mesh that will help guide the 3D mesh to small blends, certain areas of the model that you want to refine. And then, for a designer, many times you might be working in one or sometimes you would be in mixed models, right? You need a little bit of each of those mesh capabilities. And that's something that you don't always see in other designer level tools, having that capability to do all of that work. And then ultimately, like we already talked about, the mesh controls that are important for the sizing and model checking, right? Are our elements good? Because if not, we'll get some really bad results. We're always going to get a result, but how accurate are we? Are we really mimicking the real world performance? So next. So with that, I'm going to turn it over to Richard, and he's going to take you through the SimCenter FlowEFD.
All right, thanks, Mike. So here on the left-hand side, this is our SimCenter wheel. So within Siemens, our simulation portfolio is called SimCenter. So all of our products are prefixed with SimCenter. And you can see we have 5 different items here. So mechanical simulation, computational fluid dynamics, electromagnetics, physical testing, and system simulation. So broadly speaking, we have a few different products in each of these compartments, but I'm going to be talking about CFD. And a product called FlowEFD within the SimCenter portfolio. So what is FlowEFD? So FlowEFD is a general purpose 3D CFD tool. And as we've been talking about, it's really designed for non-CFD experts. Historically, it's been you need a PhD to determine what sort of turbulence model and wall function you should be using. Meshing has been very painful in the past, but this is a new breed of CFD tool which removes a lot of that pain. And because of its CAD embedded nature, it's just an extension of the CAD platform. So, here at Siemens, we have Siemens NX and Siemens Solid Edge. Those are our two CAD platforms. We also support third-party or even competitive vendors. So Creo from PTC, SolidWorks and CATIA from Dassault. So if you're using any of these 5 different CAD platforms, FlowEFD can plug in on top. And of course, we support multi-CAD companies as well. And we really like to think it reduces the overall CFD simulation time by as much as 75%. Okay, so what kind of designs can we tackle with FlowEFD? Yep. So here's the industries that we go to market with here at Siemens. So automotive and transportation, anytime you're using some sort of fluid, and remember a fluid can be a liquid or a gas. Okay, so here we got like an intake manifold, external aerodynamics and aerospace and defense applications, consumer products, something as simple as an extractor hood. Electronics and semiconductors is a big one for us at Siemens. So when you're designing PC boards, components on those boards, and then heat sinks, fans, enclosures to ensure that the electronics are going to be cool and operating reliably, and getting adequate airflow. That's a big area for us with CFD. Also things like energy and utilities. We can do combustion. Okay, so if we wanted to look at two-phase flows, boiling water, passing it over turbines, we can do that sort of simulation as well. And there's a few other things here, but med device and pharmaceuticals. You know, recently we've had a big request for air tracking within the built environment. Okay, so where does the supply air come from? How is it extracted, and where do the contaminants go? That's been a big focus area for us over the past 15 months or so with the pandemic, and making sure that clean rooms and air handling devices are positioned and operating correctly. And what happens if they were to fail? So I'm not going to go through all of the physics ranges, but broadly speaking, it's fluid flow and heat transfer. Can we remove heat with air, or can we remove heat with water? And what are the resultant temperatures that we get within our assembly? Yeah, so it's very, very powerful. As I said, general purpose, and yeah, it can be used in a really wide range of applications. Just going to highlight a couple of things. So rotating flows, for example, if you do have fans, impellers, propellers, where you're driving air or water, we can simulate those. Condensation is a new one for us. So being able to understand fluid films and how they burn off, right? If you don't want water forming on the inside of your brand new BMW's headlight or tail light, right? We want to avoid that. Filling and emptying simulations. So if you're filling a container, removing the fluid, understanding how it sloshes around within the container and what sort of forces are generated, we can do that with FlowEFD as well. And then also combustion. So burning a fuel with an oxidizer and understanding what the flame shape looks like and the amount of heat generated by that combustion process. Yeah, so really wide range of CFD applications. So I've just got a very quick video here of FlowEFD in Solid Edge, and what we're looking at is a valve. Okay, and the nice thing about being CAD embedded is that we can leverage some of the powerful CAD functionalities, such as Synchronous. Okay, here we've just made an angle change to the outlet of the valve using Solid Edge, and then you can see that the simulation is straight up to date with that geometric change. Making a geometric change like that with a step file would be pretty much impossible, right? Because we're in Solid Edge, because we've got the history and we've got the synchronous technology that allows you to make those changes, means that doing these variants is very straightforward, and the simulation stays in sync with the geometry as designed. All right, let's have a look at another example. This is an LED streetlight, and we've got a heatsink that's been designed here. And again, because we've got access to the parametric CAD features, we can drive variants such as pattern parameters, sketch dimensions. We can use our built-in optimization algorithms to really explore the design space and find the most optimum solution. What's going to get our LED streetlight to operate the coolest, therefore last the longest, reduce warranty claims, and reduce the need to send someone out to actually replace that. So, the end design might not be the most practical, but the fact that you're able to actually drive these variants is very, very powerful. And you never know, you might find something that you didn't think about, and the simulation will converge towards that optimum solution. So I'm going to hand it back over to Mike to talk about SimCenter 3D and our mechanical simulation.
Great, thank you. So as Richard showed you around the wheel for SimCenter, SimCenter 3D is our flagship mechanical simulation product, and we'll go into a little bit more detail there. So as you look at the wheel on the right, at the core of it is our engineering desktop. So all of the tasks and functions that I described early on, with being able to work with the geometry and all your pre-processing for meshing, loading, and boundary conditions, that's at the center, the engineering desktop, and that really focuses on our open strategy, both from the multi-CAD, we can open those files, bring those in and work on, as well as the multi-solver support. So you can see our tools and solutions around the wheel, everything from structures and dynamics out to electromagnetics and acoustics, all those different types. So we have our solvers, but we also could use the multi-CAD information and the multi-solver from the engineering desktop. We can actually pre-process for other codes as well. And you might ask, well, why would that be important? The ability to do both our own as well as others within one single environment. Instead of learning different codes and having to do different things, it can all be done within one engineering desktop. And then as you get to the outer part, that's okay. Yeah. So the idea is we also can perform then the multi-physics. And what do we mean by that? It's really the combination of, say, running a thermal analysis and see how that impacts our structural analysis, or taking that and using, our modal analysis and drive those results into a dynamics analysis. So it's being able to combine those different ones using the same environment for that. Also, then, and Richard will talk about this at close to the end, is really being able to wrap all of that into doing what if studies, right, or trade studies about design exploration. What if we try this? What if we try that? How do we optimize those designs? And so once you're working within a common environment, that becomes a much easier process. Next. So today we just wanted to focus in on 3 areas, but if there's something else within the wheel that you're interested in, please by all means, reach out to Rich and the Prolim team. We can follow up from there. But we're going to focus on the structures, dynamics, and durability. And so when you look at the structure side, I think most from a designer perspective, there's a lot of designers that can go in and do the linear structural analysis, right? So that might be something like the truck frame you see there, going in and seeing what if we put these loads on, what's the stress, what's the deflection on the part. It could be like the aircraft wing, right? Going in and looking at deflection, right? We're concerned how much as we assemble this, or how much the loading, what's the deflection on those parts. We also then cover things like nonlinear application, and that might be something where think of plastic parts, right? So that you could run a linear analysis on it, but because of the material nonlinearity, you might want to take it to that next level to see how that part's going to perform. Or you may have something that has a very large deformation. So if it goes beyond a certain amount, that gets you into a nonlinear solve. And so having all of those again within the single system, you can move from one discipline to the next. Also, things like the modal analysis, you might be looking at, in the upper left there, that casing, and seeing what's the normal mode of vibration of that part. How would that interact with, if we had a motor on there? Would that be an additive where both frequencies would add together and actually start to cause damage to your structure? Also, those modal analyses, those results can be driven into a multi-physics simulation for the dynamic response. So we can take that to the next level. And then other things like buckling. So if you think about something like where a very tall light pole, its length to diameter ratio is very high. And so something like that, where you're pressing down on it, loading it, what would happen to that? Could it either by its own weight buckle, fold it in half, or just by your loading, would that impact the design? And so all of these are powered by SimCenter Nastran. So Nastran is our best in class structural analysis solver, and so that's what drives the results. So from there, that moves us into the next one, which is our dynamics. So on the dynamic side, think about the things that you might be trying to solve or deal with here, right? One could be, the satellite. When you're launching that to orbit, and we're doing a lot of customers with space applications, right? Launch rockets and things like that. The dynamic loading on those designs, you can't afford for those products inside of there to fail. So you've got to make sure that you take that digital twin, perform those simulation, and make sure that it will survive launch and you don't damage your critical electronic components or other structural members, the different elements of that. And so this is a way to go in and run that. Another one is where you see on the car example on the lower left, noise, vibration, and harshness, right? You want to have a quality vehicle where the passengers are not hearing all the road noise, all the engine noise, all these different things. And so being able to use that dynamic analysis to solve for that. Another area is rotating machinery, right? The rotor dynamics. So you might have an aircraft engine, you might be dealing with gas turbines, those different types of designs. And so we have a very strong solution in that area as well to help solve and prove out the performance of those products. Next. And then the third area here is really on durability and fatigue. So if you think about that, again, for the quality of your product, you really want to prove out that, hey, we're not going to have early failures in that. And so, it's very expensive to do all the testing and run those. It takes a lot of time, a very costly process. And so, as Richard showed earlier, if you wait until the end to catch that, it's a very expensive to make those design changes. All of the costs are already built in. And so this allows us to go in and perform those tests virtually on our digital twin early in the cycle and catch those things way earlier and reduce the amount of prototypes that we need prior to launch. And so the easiest example of this is, I think we've all had taken a paper clip and bent that back and forth until we bent it and broke the paper clip, right? That's your durability and fatigue. And so many times, what questions are you asking? Well, how many times can I bend this back and forth before it breaks, right? You want to know what's the life calculation of that. You'd also like to know what factors impacted that. Was it the number of iterations? Was it the speed? Was it the loading? Was it the material characteristics? So all of those things can be answered by going through with our durability and fatigue analysis. Next. So with all of that, all the different simulation disciplines that you can run within the engineering desktop, it also becomes a multidiscipline, right? So when you start to move beyond just what we talked about inside, it might be something like the coast simulation, right? So in the sunroof example, where you're looking at a dynamic motion study, but you want to connect that to your system model, which could be a one-dimensional simulation. That control model, we want to see, okay, here's what I virtually predicted. How does it work in the real world, and get that feedback, for your electronics? How is that actually working? It also could be on the left-hand side. We talked just here about testing, right? It's a very costly, time-consuming. Well, if we've done the simulation, we want to be able to correlate those results. How does our virtual simulation look in comparison to the actual tested information, so that we can make better assumptions in our models? So it's really drawing this out to the much bigger connection to our whole SimCenter portfolio, not just, can we do a design sim? So having access to all of that and the scalability up. So maybe I do it as a designer, but you know what? I want to give this to Richard as our analyst. He can take what I've done and work from there. So a very complete, engineering desktop and simulation environment for your designers and your analysts. Next. So if we take a look at this example here, this one is really just to show you very briefly in action, right? So if we look at this, we're trying to make some determinations on the performance of the upper and lower control arms. A designer could just take that single part and you could put it in and mesh it and put loads and that on it. But in this example, we're using a dynamic motion study that we're incorporating flexible bodies into it, and it's allowing us to determine the stress on those parts much more accurately than just determining, a simple fixed, hold the part in one area and put a single load. You're getting a much more dynamic response to this, and really getting a chance to look at both, again, the stresses. You can see those parts. We used a 2D mesh on them. We also have some 1D elements holding it at the back, and you're seeing the impact of all of that motion and movement, how that really gives us a better understanding of the performance and the stresses in these particular parts. A couple other things that also get, created out of this are, you can see that the brake line, we can see with that flexible body, we can check for dynamic interference and such. So there's a number of things that from a so with that, I'll turn it over to Richard, and he'll close out with his last topics.
Okay, thanks, Mike. So I'm just going to stop sharing because I've got some audio that I need to share. So let me do that. Share again and include computer sound. There we go. I just got a very quick video just to show the actual products in action and how they can be tied together as well. So I'll just let this play.
FlowEFD for NX can be used in a fully integrated workflow with SimCenter 3D for thermal, mechanical, and thermomechanical studies. This workflow video will outline the steps of such an approach. A full authority digital engine control or FADIC unit is modeled in SimCenter FlowEFD for NX mounted on an engine nacelle. Starting with an empty unit, a populated PCB is imported to be placed inside it. An ODB++ archive exported from Expedition PCB is imported into the EDA bridge interfacing window for thermal model preparation. Thermally critical components are unfiltered and considered for a thermal simulation. In this case, all those components that are greater than 0.6 millimeters in height and 3 millimeters in length. By default, all components are unpowered. By importing a power list, these powers can be set automatically. The PCB is set to be modeled in a compact form, a lumped object with appropriate orthotropic thermal conductivity values. The thermal representation of the PCB is transferred to SimCenter FlowEFD and located in the FADIC enclosure. A fixed temperature boundary condition of 90 degrees C is set on the housing. A full 3D CFD thermal simulation in SimCenter FlowEFD predicts operating component temperatures as well as PCB temperatures. Natural convection airflow distribution within the FADIC enclosure is also predicted. The FlowEFD results are unloaded, and the SimCenter 3D pre-post interface started directly on the same model geometry without leaving the Siemens NX session. A finite element mesh is applied to the same model geometry. The casing and the bracket are using automatic mid-surface 2D meshing technology, and the electronics components are meshed using a combination of 2.5D and 3D meshing approaches. A dynamic analysis is conducted with a sinusoidal excitation of 20 Hz from the center. After the solve, we can directly open the results on the same user interface and define post-processing activities. At this stage, we're able to define the mechanical stress on the bracket and the acceleration on electronics components. Transient von Mises stresses are predicted and shown in the support brackets in the PCB. The analysis identifies where the increased stresses are located so that remedial action can be taken.
So that was just a very brief video showing the two products that we've been talking about in action, and that was the NX version. But exactly the same thing can be done in the Solid Edge environment also, and other. We can import other CAD files as well into the SimCenter 3D engineering desktop. So what I'd like to talk about next is Teamcenter for simulation. So up to this point, we've been talking about 3D CAE and how we can perform structural and CFD simulation on your designs. But one area that's often overlooked is data management. Okay, so what do we do with all these files that are generated when we perform this simulation? So if you imagine an analyst, he's going to be working, if we think about a typical unmanaged analysis environment, there's going to be requests from designers and program managers. They're going to come into the analyst, and that analyst will then go ahead and extract data from PDM system manually. He'll get requirements, maybe in an email or a Slack message or something like that. He will then fire up simulation applications again manually using his preferred methods, and then store the data, the models and the results, maybe in a shared network drive or something like that, so it's backed up. And as you can see, it's quite a disconnected process, and the problem really multiplies itself with the addition of multiple analysts. Everyone could be doing things slightly differently. There's no revision control. It can get into a mess very quickly, and if you're trying to pick up someone else's analyses and work out where all the files are, it can be an absolute nightmare. So here at Siemens, we have a data management software called Teamcenter. It's a PLM solution, and we do have an additional add-on for simulation purposes. And what this is a single source of truth, and it manages not only data, but also simulation tools, workflows, all the requirements, the results, everything is managed in a single environment. So all the requests go into the simulation management system. If any updates or changes are required, they're made in the system and tracked. Okay, that's the really important part. The analysts will then dip in and out of the single source of truth to perform their analyses, and then designers and program managers will use dashboards on top of Teamcenter for simulation to check the results and check the progress of where we are with the simulations. So, and it can also control the applications. So it's a much more controlled way of performing simulations because, as I said, a lot of files can be created, very large files of that can be created when you perform simulation. So if you think about the designed geometry that the CAD team has created, or maybe yourself has created, maybe it looks something like this, part of an aircraft landing gear. When you then go to perform simulation, there is a level of simplification or at least some sort of modification that needs to be performed on that geometry before it's ready for analysis, right? So maybe you remove some of the parts that aren't needed. So straight away, we're deviating from the original CAD geometry. Then we mesh that. Okay, so again, we're moving from a CAD geometry to a FEM model. They're still connected, but they are separate files. Then we add the loads and the constraints, and then finally we have the CAE results. So just here we got 5 different file formats, 5 different files that we need to deal with, keep track of, and if there's any revision control that needs to be done, typically or historically that's been done manually. So Teamcenter for simulation not only does data and lifecycle management, as I touched on in the slide before, it can also manage the structure of the simulation, right? Are we doing a static, a dynamic, a fatigue analysis? Are we coupling that with CFD? Are we calling on multiple solvers? How is that all managed and licensed? Teamcenter can help you there. Simulation tool and process management. So it's not just the Siemens tools. Teamcenter for simulation can be used to drive competitive products. Maybe there's an area that you need a specific solver from another vendor. Teamcenter for simulation can work with those as well. And then finally, results visualization and reporting. Is there a standardized format that your engineering team is expecting the results? We can standardize that in Excel or PowerPoint or a dashboard to make sure that the results are, at a glance, exactly what you need without having to open up the tool, load the results, and manually dig into there yourself. So it's a very, very powerful tool for controlling the entire simulation process. So here's our SimCenter portfolio. We've touched on the mechanical simulation and the CFD portion of things, but just to kind of highlight that it is much larger than that. So we have system simulation. So as you zoom away from the part and the sub-assembly model, as we look at the full top-level assembly of, say, an entire car or an aircraft, how do all the sub-assemblies, the system of systems work together? So we have programs like SimCenter AimSim and SimCenter FlowMaster that can do that for you. Then we have our more traditional CAE tools. We saw today SimCenter 3D and SimCenter FlowEFD, but we also have much more analyst level tools that can dive a lot deeper than these designer level tools. And then we also have physical testing hardware as well. So if you do need to do, lab testing, vibration, or thermal testing of your products, then we've got hardware test equipment that can measure, log, and again keep track of all of the physical test setup of your testing. So we talked about Teamcenter, which can tie all the data process management together. What I'd like to finish on is the exploration and analytics using our HEADS product. So HEADS is a multidisciplinary optimization tool. It can be used standalone within a single tool like FlowEFD, or it can be used to chain together multiple products and drive an optimization feedback loop from start to finish. Right, it's very, very powerful and overlays on top of the entire SimCenter portfolio. So let's take an example of this IGBT module. An IGBT is used to control high power electronics, such as a motor. Like think of a motor in a Tesla or an EV. You need these IGBTs to control the current that's going to this motor, and they get very, very hot. And what we'd like to do is optimize the liquid cooled heatsink pattern that's going to be machined out of aluminum at the bottom here. So we've got a pattern that's been preliminary designed in CAD, in NX, say, and what we need to do is tell HEADS what the design or optimization criteria are going to be. Okay, so we want to reduce the temperature of these IGBT chips. These are silicon or silicon carbide, but we also want to reduce the pressure drop. So these are actually two competing goals that we're trying to find an optimum for. Right, we want the fluid to get through there with as little reduction in pressure as possible. You don't want to get the water to fight through lots of fins, but we also want to keep the chips as cool as possible. So with that, we can specify the goals. We can tell HEADS which parameters it can change, such as the pitch of the pattern, the dimensions of the diamond, the material choice, and also the flow rate through the system. Okay, and then the software will go through and try a lot of different variants for you. Again, this is just in a single tool, right? And say that the software finds an optimum, it can then pass that to structural, it can pass that to the system simulation, and all of that is controlled and driven by HEADS, and the data is stored in Teamcenter for simulation. So it's a way of very painlessly performing these what if studies without having to manually set them up, keep an eye on things, because HEADS is designed to form these variants, keep track of them, and intelligently store that data. So very, very powerful. And it's often a stage that's overlooked in simulation. Most people perform the simulation, get the result, and then maybe manually go back and change things. But HEADS adds a lot more intelligence with our Sherpa algorithm for the optimization. So here we can see really the ROI for not just simulation, but really the Siemens SimCenter offering. Modeling the complexity, as we saw, all the various types of meshes that we can handle, the engineering desktop from SimCenter 3D, wide range of disciplines, structural, CFD, EMAG, system simulation, physical testing. We can explore the possibilities, right? So heats with the intelligence to drive all the variants. We can go faster by automating things, by managing the data. The fact that it's for design engineers to perform this means that you don't have to wait for the analyst team. And again, staying integrated. Teamcenter for Simulation controls everything, controls data revision and simulation process management, requirements, and results visualization and reporting. So yeah, SimCenter is really a very well-rounded solution, which, as Mike mentioned, you can start with the simulation for designers, but then there's an upgrade path to the full, analyst level simulations where you can pass that data and work, add on to the work that's already been done. So very, very powerful way to start, getting into CAE simulation. So yeah, I'm just going to finish on this slide, and I'd just like to say thank you for your attention. Rich, I just want to hand this back over to you to see if there's any questions.
Great job, Richard. Thank you, Michael, as well. Excellent presentation. A lot of material we covered in a very short period of time. So I want to open it up to questions for the audience. I know there was a lot of topics we discussed, but if you have any questions, feel free to unmute yourself and go ahead and ask away, or you can type it into the chat as well. So one question I did get from one person was, how do you automate common designer CAE processes with SimCenter 3D? Richard or Michael, either you can maybe
Sure.
answer that.
Sure. Let me take a crack at that one. So there's really two things, two paths you could take with SimCenter 3D. One is we have a very robust open API. So if you have people that like to write automation code and want to automate repeatable processes, so that they could put it in hands of the designer, and they maybe only have to make a few selections and the rest of the system is doing all the work for them behind the scenes. You can do that with our open API. You can write in languages, .NET, C# and others to write code to help automate. So you might have just a few buttons inside SimCenter 3D, and that designer walks you right through that. The other is in NX and in SimCenter 3D, you have file new templates. And so you can actually use those templates to help put other information into them to help automate and help guide the designers through that process. So one is the code based, and then one is the template based that we use. And that could make it very direct and guided for your designers.
Great. Okay. Thanks, Mike. Any other questions from the audience? Another one I got here is, how is SimCenter 3D licensed? Richard or Mike?
Sure. So I can talk about the SimCenter 3D, and then if Richard would like to put in on the FlowEFD. But for SimCenter 3D, we have a bundle that you would have. So it would include some design capability, the pre and the post processing, and the Nastran solver inside of that. So you could buy it as a bundle standalone. You could also purchase it if you already own seats of NX Design. You could purchase it as an add-on. So that would be just the pre and post processing capabilities and the Nastran solver. So standalone bundle, an add-on bundle. And then the other piece that we add some flexibility for you is something called our SimCenter tokens. And the idea here is you basically purchase a pool of tokens, and those can be used to run the different solvers. So as we saw, you would get the base functionality like the structures and some thermal, but you might want to run some of the other disciplines. The tokens, without having to buy each and every one of those, if you have a set number of tokens, say 50, and you wanted to run, you know, for instance, the acoustics, or you wanted to run the magnetics or one of those other ones, that user would run it. When they're done, the tokens go back into the pool. So it's a very flexible way. Instead of you having to buy maybe 5 add-on licenses, you could just buy the tokens and then use each of the individual solvers or capabilities whenever they're needed.
Okay, great, thank you. Looks like I got one other question here. What types of multi-physics solutions are supported with SimCenter?
Sure. So on the SimCenter 3D side, as we were looking at the disk, the circle, you know, there's the thermal mechanical, we have thermal fluid, we have a fluid structural, and then combining those, we have a fluid thermal structural analysis. We also have a vibroacoustic, and then the motion structural, like the one that I showed in the movie there. So
Okay.
those are some of the key ones that you would have access to within that from the multi-physics.
Okay. Any other questions from the audience? Feel free to unmute yourself if you have anything you'd like to ask. I'd also encourage you, if you wanted to take it offline, feel free to reach out to your sales rep. Brandon is still here online. Brian, I think, just dropped off. Or you can reach out to myself or any of the folks at Siemens. Again, Michael and Richard, thank you for your time this morning. I know we're right about on the hour now, so I think we will wrap up at this point. But we appreciate everybody's time this morning, and if there's anything we can help you with, please reach out. Thanks, everyone. Have a great day.
Thank you. Bye.
Thanks. Bye.